Three of us must. How about four? Anything you guys want to point out? Everything is. Any questions? What's the homework going?
Good so far.
Nothing that might be useful to discuss in the class.
Go over. Hamiltonian's principle of stationary.
Yeah, we will be doing that today. Yeah.
Yeah, and
So
Hamiltonian equation of motion. I did calculate that in question 3B.
yeah, we will go through it. It's a relatively abstract. Okay, so hopefully others, I don't know. Susan, Monica, maybe the bus is late. Do they come by bus?
They come here or maybe.
Oh, okay. So maybe, then we should wait. So we have been pretty much trying to ask, given the equations of motion, like any equation you can think of, can we think of it as a minimization principle? At present, we are doing Newton's laws of motion, and we are asking, can we think of it as a minimization of some physical quantity? And it turns out to be the action. And we said the integral of the Lagrangian is what it is. So we said action. So first let's say Lagrangian. Lagrangian turns out to be a function of position. It is in general a three-dimensional position, that is x, y, and z in it. So this is written as a vector. And they are all functions of time. These are the trajectories of a possible trajectories of a particle in space. So it can be x as a function of time, y as a function of time, z as a function of time. It also depends on the velocity. So this is d by dt of x, and it is important to realize that it is x that is the independent variable. Velocity is basically the derivative of that function. In the Lagrangian statement, we will be talking about Hamiltonian statement, Hamiltonian principle, and then very in passing, we will also talk about Schwiнгerian statement. In all those, the velocity need not be dependent. In those Hamiltonian and other places, it is independent. Hamiltonian is always a function of momentum, and as we will see, I mean, why it is, I'll come to that. So that's Lagrangian, if you want. So this is L. Okay, so that is, since we are not integrated it yet, so it has an explicit dependent on time. Then we have action. Action is defined as W, like these things change from textbooks. It's most of the textbooks use the action as S. Right, that's common. But most of what I am doing is based on Schwinger's ideas. This is if, for example, you might see that Schwinger's textbook is the closest to what I am doing, but at the same time, it's not a classical mechanics textbook. It is electrodynamics, it is quantum mechanics. So those are what he has taught, but these are all ideas that he developed, he himself developed, and that is Schwinger's, and he uses this W, so I use W, and it's not very uncommon in quantum field theories. It is common, but he used W, so it's a variable, it's not a significant, I don't think it affects anything. So this is an action, so this we say is a depend. Here is where you say what are the dependent quantities. It's only X, V doesn't show up. You only change X, you don't change V at this stage. If you want, you can say it depends on the endpoints, T1 and T2. That's equal to T1 to T2, T tangent of X, the function T. I'm going to use the notation here as V. This is only for simplicity, I'm using V here. When you're doing Lagrangian, V is not independent, it is dependent on the position. That's T. Okay. Notice again, T doesn't show up on the left hand side, it only shows up at T1 and T2. If I fix my T1 and T2, if I say what is the possibility that an object dropped from a height Z1 reaches the height Z2, I fixed those two quantities. Once I fix it, then these two are gone, right? T1 and T2. I'm at T1, I'm at Z1, at T2, I'm at Z2, these two are fixed. Later on, we will see that this also has information in it. We will talk about that very quickly. Within few weeks, we will talk about that, but most of the early weeks, we have this T1, T2 is not there. So often you will see in homework problems, we close the functional derivative brackets right after X itself. So W is dependent on X, and that's your action. And we said minimization. So this is stationary action principle. So you can ask what replaces Newton's laws. This is what replaces Newton's law. This is the principle. Like we are not saying Newton's law is fundamental anymore, or one of the ways you can present it is that Newton's law is not fundamental. It is this that is fundamental. And the statement is that the action against suppressing T1 and T2, I can write T1 and T2, but I'm suppressing that just for simplicity. And with respect to X, since I've used T, so this is T prime. With the action, the functional derivative of the action, or think of it as if you make a small change in the trajectory, X is a trajectory, small change, small variation. If the action is zero around that variation, that implies something, and whatever that implies is your Newton's law. So this implies, so let's say this implies, in general, if it was any like any functional functional derivative, it gives you what is called Euler-Lagrange equation. But for the particular, or did I say that correct? Yeah. If you start with the Lagrangian, where Lagrangian is typically kinetic energy minus potential energy, but not always. Okay, we will see situations where it is not kinetic energy plus potential. In the simple situations, it is. So Euler-Lagrange equations, these are basically Newton's. For the case of the Lagrangian, it's basically the Newton's laws. And that reads, and derivative of partial derivative of the Lagrangian velocity, again, velocity is the time derivative of position, that's equal partial derivative of x. This is a gradient, when I write derivative with respect to x, that's your gradient. And in the mechanics problem, this is nothing but Newton's law. This will often be the momentum, so maybe few more definitions. So canonical momentum is equal to P equal to partial derivative of L with respect to V. So once you have the Lagrangian, immediately take the derivative with respect to velocity and you have momentum. The example is straightforward example is is Lagrangian is equal to half m v square, write it as v dotted with v, so that know that there are two velocities in there, and in general, the potential energy can be a function of velocity also. Notice if the potential energy is a function of velocity, then this partial derivative will hit that potential. Often, not necessarily all the time, this is not velocity dependent. If it is not velocity dependent, so if u is not velocity dependent, then P is equal to mass times velocity. Give an example of a potential energy that is velocity dependent. Which force has potential energy having velocity?
What potential has force but not velocity?
No. I said a potential energy associated with a force as well. Let's begin with the following. Which force is velocity dependent? Give me an example of a force that is velocity dependent. Lorentz force, any other force you can think of? That is velocity dependent. Good. Lorentz force is magnetic field, QB cross B. Good.
Newton's second law.
No, that's on the left hand side, right? I mean force. Like that is acceleration, you mean d by dt of mv.
Yeah.
Right? That's acceleration. Like that's the effect, if you want. What is causing the effect is the forces. Give me an example of a force which is having velocity in it.
Okay.
Good, right? So that's where you see like homework 1, we see drag forces, quiz. You have, I mean, as last time we did, given a force, we tried to calculate the Lagrangian for it, right? Find the Lagrangian for the drag force. And I'm thinking of doing something along that line as the question number 1 for your midterm one. So that gives you an idea. So put in more effort in that. Okay. Is that clear? No. Ask you know. In midterm one is next week, 1 week from today. The first question I'm thinking, like I'm considering making it out of this quiz. The quiz that I gave just now is what is the Lagrangian for a drag force. Something associated with that will show up in your as your midterm one question number 1, right? There will be 5 questions. Now I gave you 3 questions, correct? So 1 is on functional derivative. Any function functional I give, you have to calculate the functional derivative. Second is do the functional derivative ab initio. You have to prove it. Like don't use the simple statements, you do the functional variation and try to do that. And now I've given you the third one. It's associated with Lagrangian and drag force. Okay, so read up the literature, whatever is available, and it'll be conceptual.
Two more questions.
Yeah, two more questions. That's assuming it's 5. Yeah, usually I try to restrict them. Yeah. I'll try to write this down on the, like I say something like preview or something and then put it on the. But this is sufficient. Like, it's basically the idea is that you want to go through. And that will be a Hamiltonian and Lagrangian problem most. Make it 5 quickly. Okay, so again, notice if there was a derivative with velocity, if this was velocity dependent, magnetic field is a scenario where it is velocity dependent. We will write down the magnetic energy for that today. And in that case, this is not MV and that can be an additional term. Right, and that's a hint for or think for the drag force also that's velocity dependent, right? So one has to be careful. Have you ever thought of like in your textbook, have you ever seen potential energy for a drag force?
I didn't know.
So those should be the thoughts that should come in.
Thank you. I didn't.
Yes,
So
so,
obviously in the book I didn't.
so yeah, so think about it. Okay. Okay, so we have canonical momentum and what else am I missing? So yeah, this is typically what will gives you the Newton's law. You can sort of see it. This is mv mass times velocity, and this will be the force. Right, this will be the force, that will be your momentum, and derivative of momentum is the force is Newton's laws. Correct. That's what we want. So let's do an example. Electromagnetism is a sufficiently successful example, right? I mean, in case you're not aware, it should be pointed out that among all the theories we have studied, if you can think of everything humans have developed until now, often you can think of success as you do an experiment and you do a theory and you match them. Right? For example, you measure gravitational field at this point, it is 9.8. Go to the lab and actually design an experiment and measure it, and it matches. That's a success, right? That's great. Like we understand that. So the best we have achieved in this manner of doing an experiment independently with the theory and matching it is in electrodynamics, and we have matched it to 20th decimal, like 9.8. Think of a number. It's usually the magnetic moment of muon. That's the most precisely measured quantity, and it has been measured to 13 significant digits, and that's an electromagnetism. Quantum electrodynamics, we need quantum mechanics for that. That's pretty successful theory. So let's do an example in quantum electrodynamics, or not quantum, but let's say classical electrodynamics. There's a good bit. Oh, I did move it already. Move again. So let's talk about Lorentz force. One should say, what is the difference between Maxwell's equation and Lorentz force? Maxwell's equation deals with the idea that give me the charge and the current. That a charge is moving, an electron is moving around. The question asked is, what is the electric field? What is the magnetic field associated with it? So give me the source or charge and current. Maxwell equation helps you calculate the electric and magnetic field. Lorentz force is exactly the opposite. Give me the electric and magnetic field. Lorentz force will tell you what the electrons will do in that field. In general, these are not coupled. Right? Electrons continuously change the electric and magnetic field, and the electric and magnetic field continuously affect the electron and proton, positron, if you have. So it is a coupled problem. The way we are dealing with it is we are decoupling it. So it's an approximation in many ways. This coupling is what is called quantum electrodynamics, where one affects the other. Like often when you're talking about a planet going around the sun, planet affects the sun also. But often sun is so heavy that to two significant digits, it's okay to not talk about the sun's motion, right? It doesn't affect it to two significant. But if you want a 13 significant digit precision, you have to take care of both. So here we are not going to talk about electric and magnetic field. The effects, electric and magnetic field is given. Like it is not getting affected by electrons movement. So in the first approximation, that's not changing. So Lorentz force is d by dt of mass times velocity of the charge that we are talking about is equal to Q times the electric field. And electric field can be R and T dependent. So we're going to keep, it's not a uniform electric field in general. We can have anything, and this is Q times V, where V is the velocity of this charge. We are talking about one charge in an electric and magnetic field. That's a velocity, and it is moving in not necessarily constant uniform magnetic field. That's your Lorentz force, and our goal is to write the Lagrangian for this. Okay. And again, these are background fields. This is given, it's fixed, so it's only the velocity of the charge and the position of the charge that is important. Immediately we go to whenever there is a force, we think of energy, but then in Maxwell's equation, we already have these ideas that electric field can be written as whenever I write E now, it's understood that there is R and T, correct? It's a position and time dependent. And that's gradient of a scalar potential, right? That's voltage if you want, right? If you're in the lab, if you measure this quantity, that's what voltage is. Often in introductory physics, you will use the letter V for that. But somewhere we start using phi, nothing special about it. You can use any variable you want. Right? So that's electric field. Is that completely correct?
That's for electrostatics.
That's for electrostatics. Very good. So what is it in general? This is not statics, it's time. How do I correct this? So this is not always correct. Huh? Yeah, so this doesn't take care of magnetic field effect. So how do you change? By adding a derivative. By adding a derivative, very good. So this is time derivative of, there is a vector potential. Both of this are R and T dependent. Maybe I should write it down first time. Seeing this, you should have seen this, by the way.
Yeah,
I'm not trying to teach this, so expectation is that you've seen this even before graduate level electrodynamics. Phi is the scalar potential. So usually you say scalar electric potential. And A is a vector magnet. We are talking, our context here is energy. We are talking, this is the electric force, that's a magnetic force, electric force, magnetic force. This is where the electric energy is. When we talk about potential energy, that's where the energy is. And this is correspond, this will lead you to the magnetic energy. So it's not, A is not completely the energy, but surely it's a potential that contributes to the energy. That's electric field. And what's magnetic field?
this is.
Curl of A, very good. And that is always true, right? That is no. You never, there is no electrostatic piece and magnetostatic piece. This is always true. And it is necessary because the divergence of B is 0, this statement gives that immediately. This immediately implies that the divergence of B is, in that sense, it is necessary, right? So we use this in our Lorentz equation. Lorentz force equation, that's equal to Q times. Let me say minus of gradient of Q times phi. It's understood that there is R and T dependence, and minus of d by dt of Q times A. Okay. That's this, and next I have plus Q times. We maybe pull it inside, the Q can be pulled inside, right? Q doesn't depend on position, time, and let me write this as dx by dt, right? So V is dx by dt crossed with magnetic field, it is del cross A, and I bring in the Q with it. Nothing special, that's just placed to, I have to write Q somewhere. I just wrote it right next to it. So I didn't do anything, I just use this, substitute it in there, so nothing significant. Again, it might help to what is my motivation. Remember, I am trying to get a Lagrangian for this, right? Lagrangian, usually, you want to look for an equation of this kind. Okay. If I want to identify a Lagrangian, it helps if I can write an equation in this form. That means something with a total derivative and something with a gradient. This is a gradient on the right side. So isolate all total derivatives, isolate all gradients, right? That's the idea. So remember, force is equal to negative gradient of something, right? Potential energy. So I'm trying to look for gradients, like any gradient will help me identify potential energy. So I already see the one gradient at least. I think that's a gradient, but then rest of it doesn't seem to be. And remember, total, I should emphasize here, what's the difference between total derivative? Like I think we know this. So let's say this is f of x of t, and t will be equal. What's the difference between this and this? Maybe let me say. What's the difference? In this case, it hits only on this x. It doesn't care for this time inside it. Also, it is just basically partial derivative of x, f with respect to x. That is all that you do. Oh, no, I didn't mean that. Sorry. I think I meant partial derivative of time, right? X is sort of clear what is happening. So this is what the difference between partial derivative of time and total derivative of time. There are two places you see time in it. The total derivative will hit both. The partial derivative will hit only the explicit t. Anything inside, it will not try to look at. Okay. So this will be equal to maybe, how can I write this? So this will be, so dx. So first do the partial derivative with respect to x, and then do the chain rule dx by dt. That is how I hit this time. And there is one more piece in there, that is df by dt. Right. So first it hits this, and then it hits this time. That's the partial derivative, and this is the partial derivative with time, which is just looking at this. Like you must have seen this before in somewhere or the other, but it plays an important role in these considerations. Okay. Okay, so iris is space. Okay, again, our goal is to get some gradient form, and notice I want total derivative in time and gradients. This is a partial derivative in time, and this is not even anything, like this is not gradient coming in. So we exploit our vector properties and expand that up. So expand that curve out. You have gradient q times 5, that's good, and this is minus a partial derivative. This is not, it's not clear what we want to do with this partial derivative time at this state. This is a cross b cross c, and remember this is a gradient operator, so one should be very careful. If, how many of you have done math methods? I think some of you have done math methods. We do spend a good amount of time in it. E&M also we spend a good amount of time in it. Pradeep and Fuza, you should try to fill in and see how we expand this. Otherwise, I'm going to write this in few steps. Make sure you get what I'm doing. We usually say back cap, so as far as you don't change the positions, it helps. So we have this is my first operator, but that has to hit on the q dot times a, and that is dx by dt. This is dotted. So remember a cross b cross c is equal to back cap, right? That's how you will say. But by doing this, what I've done is I moved my a to this, a inside. But if I move my a, then gradient has to act on that. So one should be careful. And then there is cap, so the best way is to say, in this case, a dot b. So when I can write c on that side, but then that will be pretending that c commutes with a and b. This is the velocity of the charge. Right. How does the velocity depends on the coordinates? Velocity is a property of a charge. Right? X, Y, Z is where you are. Velocity is how fast you're going. So it should not depend on coordinates. It's a fundamental property of a charge itself. If you have a charge density, you say that, oh, this point has another velocity, this point has another velocity. Velocity of a charge is not a coordinate dependent quantity. Okay. So because of that reason, you can take this into the gradient. That's like saying this should be written as A, B, C. Is that clear what I mean? This is the dot product. In the back cap, A and C are dot product. In this way of writing, the advantage is that I haven't operated or I haven't moved A into B. Think of quantum mechanics. If think of matrices, A, B, if A, B, and C are matrices, then I cannot move them around. Right? They don't commute. So then I have to be careful. A gradient operator also is an operator. So I cannot move things easily inside. So I should be careful if I move the A inside. But the argument is that this is velocity. Velocity of a charge does not depend on coordinates. Right? That's the property of the charge. Right? Wherever it has its velocity. So it can be taken in. So because of that, this can be written as gradient now. It is what we were, and now I'm going to think of this as velocity for at least in this equation. So this is Q V dotted with A. And it is hitting on both. Now I have back. So this is the back term, right? B, which needed some justification that why did the velocity go in? Not always it goes in, especially if there is a distribution of charges. If this was not a point charge,
if this was a distribution of charges, then this doesn't go through, and then one has to be more careful. Minus of, I have to now A dotted with B times C, so this is V dotted with the gradient times Q A. Is that clear? Any questions at this stage? And still in our mind, we are having gradient and time derivative in mind, right? So at least I have two gradients now. And I'll keep that, so, and I'll move everything to the left because I sort of know what is going to happen, but it's not clear for you guys as to why should I move it to the left. So I'm going to move everything else to the left, so it is plus time derivative. And let's say plus V dotted with gradient operating on Q times A. Now that's equal to negative gradient Q times 5. Charge times voltage is energy, potential energy, electric potential times charge is potential energy, and the magnetic energy, it is velocity dotted with a vector potential. Notice the negative sign here. This is going to become the potential energy. Okay, very quickly, within a few minutes or within a step or so, this will become the potential energy, electric potential energy, magnetic potential energy. Notice there is a difference in sign. Difference in sign has to deal with Q times velocity can be thought of as current. This is a charge. This is a current, Q times velocity. Like charges, do they repel or attract? Repel. Think of currents, like currents. Have you heard this? If you have two currents, two like currents, that means they're in the same directions. Right? Do they repel or attract? Attract. They do opposite of what electrostatics does.
Like charges?
Like charges repel. That's correct. But I said like currents.
Oh,
Like currents mean
Oh.
if I have two currents going in the same direction, I1 and I2, this is a, sometimes we also do experiments related to that. This creates a magnetic field. Like magnetic field here, it goes into the page here, and then there is velocity crossed, so this attracts, right? That's the force. This is a magnetic field. Is that clear?
Yes.
So like currents attract, like charges repel. That's because of this negative sign. They do exactly opposite. Okay, so that negative sign is what explains that behavior, that why should like currents attract at some level. If you were to address that question, that's why that happens. Okay. So it seems like, okay, we have something with a gradient. What about this? I said we should identify everything with a time derivative. What is this? This operator should be familiar in partial, what do you call it? Partial derivatives, partial differential equations. Yeah. So what is that? No. Let's take, we just now said f of, let's say x as a function of time, let's say x alone, right? And t, right? So that's a function, let's say, let's do total time derivative. What is that equal to? Tell me. Partial derivative of f with time, so that hits this. And then I have to hit the other time. What will that be equal to? And dx by dt, right? Now there is only one variable, so I don't have to differentiate between this. If this was a vector, right? So then there is a y also, right? dy by dt plus z by dt, correct? That's a dot product, right? That's equal to dt plus partial derivative. That's a dot product. I write it as a gradient, so it's r, right? Gradient. And this is velocity, right? Dx by dt, dy by dt, dz by dt. It's velocity, right? So it seems like this is partial derivative of time plus move the velocity on this side. Gradient of an f, right?
You can move the gradient, move the velocity of the.
Velocity, this is a derivative, we were acting only on this, right? This is only on, I could have done this the other way also, it's just a way of writing. There is no, like usually they commute, put it like that.
Okay.
Yeah, you can ask the question, what happens if f and x does not commute, but it will because f is built out of x, right?
Yeah.
So if you are talking about a non-commuting object, then one has to worry about that, but x is here commuting, yeah.
But then, you know, you need a matrix or anything.
Or an angular momentum, if this was angular momentum, then you have to worry about it. Because angular momentum components do not commute, right?
Yeah.
Right, so then one has to worry about, and that is, we do worry about in quantum mechanics. Okay, so it's good to see that this is nothing but a total time derivative, and that's what we were looking for, right? So this whole thing is a total time derivative. So have time derivative of mass times velocity of the charge plus this is, remember again, this is A, it doesn't have any velocity dependence. Let's highlight that fact. A is a vector potential that is built out of positions. Like we don't say that there is a velocity in there. One could ask, like this was at this stage an arbitrary function at basic, right? Which helped us give us our magnetic field. What if this was velocity dependent? Quiz, okay, but usually in the classical electrodynamics, this is position dependent. Okay, you could ask, is there any freedom we have to introduce a velocity dependence in? Does Maxwell's equation allow the vector potential to be velocity dependent? Okay, so that's something you can explore, and this is equal to negative gradient option. What?
The quiz question.
Oh, quiz question, yeah, you guys. You can go back and look, right? What you should say is the time. This is what I would do. I would note down the time and then go back and go to the, but even that is too much work, I suppose. So you have to go and search for that recording. Too many clicks, yeah. You should not have quizzes. You should stop with. Okay. Again, this is R and T dependent, maybe emphasize on that because this is the main statement here. Q V dotted with. So what is the potential energy associated with magnetism? So then you would say it is this. You often hear the statement that what's the work done by the magnetic force? Work done by a magnetic force, is that, have you heard this question before? Work is force dotted with distance, right? Displacement.
If it's a close.
Force dotted with displacement. Don't make it a closed. Let's say a magnet lifts a car, puts it in here. Correct. So you can ask the question, how much work does the magnetic field do? Very reasonable question to ask. Correct. And the argument would be, someone would argue, before, so you, let's say you are an engineer and you want to design a equipment which takes a magnet, builds a or lifts a huge car and drops it on the other side. Someone who is an undergraduate physics student comes and says that I'm not going to approve that because I know that force is QV cross B. Force dotted with displacement is how much? This force dotted with displacement is how much?
0.
And why is that?
You take the curl of a dot product.
Curl of a dot product, it is 0. So the work done by a magnetic force is 0, right?
In other words, when we
Yes, so how does a magnet lift? But I do see magnets lifting the cars and putting it down, right? How do they work? Right, so that could be an argument someone might pose, saying that, oh, what happened to the our work right here? There, you go back and say that there's this piece also does. Potential energy typically is thought of as only from here, the gradient of the force, right? I said earlier that great force is equal to the negative gradient of potential energy. That's too simplistic. Many of the forces like gravitational in all the static cases, force is negative gradient, but here it's not. Here it changes the momentum. Just the fact that there is a magnet in there has changed the momentum question completely. So yes, this piece is work is the gradient of that is contributing, that is 0, but there's more to it. So that analysis is hard. So that's okay. So what we have said is that this is now Lorentz force. I have just manipulated my Lorentz force and returned it in this. Our goal was to get the Lagrangian. Correct. But now I can compare it with Euler-Lagrange equation. Okay, so that's what we will do next. Okay. So we want to compare this with d by dt of a canonical momentum, which is the Lagrangian, a partial derivative of Lagrangian velocity, and the gradient with respect to position. Right. So compare the two, immediately I know that I can see that the partial derivative of the Lagrangian with velocity is mv plus q times the vector potential. And I think in all these discussions, it is good to point out that even though this seems to be very clean here, the way I'm writing it, it has this problem that the scalar potential and vector potentials are not unique. They are gauge dependent. Like usually mathematics is useful only if you give a unique answer. Like if you do an algebra quadratic equation, you get a solution which are two numbers. If I tell you that no, these two numbers, maybe sometimes it is -2 and -3, but sometimes it is also -7 and -9, that's not useful. Like that, or at least it's not very useful, then I should know when to pick which solution, correct? So similarly here, these are not unique, there is this gauge transformation which can disturb this. One of the gauge transformation is voltage, if you're an electrical engineer, you always ground it, right? So it's a ground dependent quantity. So when you say voltage is 110 volts on one side, you're saying the other one is 0. I can always say it is 220 and the other one is 110. That's perfectly fine. It's a difference that matters. So this is a reference frame dependence, right? That's a very simple case. The vector potential becomes more involved. There are more arbitrariness in there. Okay, so has that, or it makes it life harder when you're doing the mathematics associated with that. So that's for your information. We won't address that. That's somewhere in electrodynamics. You do that. Here we just say this Lagrangian derivative of the Lagrangian with velocity, the gradient of the Lagrangian with respect to velocity is so much, and the gradient of the Lagrangian with respect to position is equal to just oh, it is with the negative sign, right? So we should be careful there. So just with the negative sign. So that's negative q times so scalar potential plus so scalar built out of current and vector potential. Oh, I didn't write this correct, right? Wrong. Sorry. This is supposed to be inside, right? Because the whole thing is this, right? So,
Gradient.
yeah, so I should write this negative gradient of q times, my bad. So minus of q b. Thank you. Okay. The first case implies, the first relation implies that the derivative of something is linear in velocity. And this is basically not having velocity at all. Right, this is constant as far as velocity goes. So I can say Lagrangian probably is half mv squared, because when I take the derivative, I get mass times velocity. And this one is a constant vector. When I take the derivative, it should give me that constant. So it must be plus q v dotted with a, right? When I take the derivative with velocity, I get the a. Correct? So that's what it should be. But then in this way of saying, I will always miss anything that is velocity independent, correct? So I could have a whole piece there which has no velocity in it. Do the same thing in here, but here it is easier because it's already gradient this is gradient, right? So gradient of Lagrangian is gradient of something. So this must be the Lagrangian, right? So this implies that the Lagrangian is equal to minus q times phi and plus q times v dotted with a. But this time, since there is a gradient involved, I can have anything dependent on v, right? That's a gradient with position. It has to be independent of the position. So it is velocity and time.
Could you explain the second one where velocity time?
This one? Oh, this one. Oh, so let's think of this, so D. Let's say L is equal to V dotted with A. Right? That's equal to Vx, Ax plus Vy, Ay plus Vz, Az, right? Do derivative with respect to Vx. That's Ax, right? It doesn't see this, it doesn't see this. What's the gradient of Vy? Is Ay and Z is Az. I will write this as gradient, not with position V of L is equal to I hat d by dVx of L times L, and that's nothing but now I hat Ax, right? Az, that's my vector A. Correct, so that's about this. So often when you compact it, you kind of miss it out, but that's all. I mean, straightforward statement. It's just might not be used to seeing it. That's all. Nothing great. Okay, good. Helps. Okay. Again, this is what you see in the math methods course. In the first 2 weeks, you get used to these things. So it's because you're ahead of yourself. So okay, together it seems like this could be this, and this could be this, like maybe this one, right? F1 could be this. So the total Lagrangian apparently could be, it's Lagrangian, could be half, and then we have to check it, right? Half mv squared plus q v divided with a minus q5. Yeah, let me not change. So minus of q5 and minus of qv divided with a. When you think of Lagrangian as kinetic energy and potential energy, that is this feeling that, oh, this is the potential energy. But remember that this contributes to momentum also. That's perfectly fine to think of it as potential energy. Yes, it is potential energy, but it changes, it's a velocity dependent potential energy. That's not common, velocity dependent potential energies. Okay. Okay, so that's good. And quiz, right? Complete such find dl by dv, like do the reverse, right? And then find dl by dx. And then check that Lorentz force is indeed is that clear what I mean? Like, show that this indeed gives you the Lorentz force, right? We did the reverse of, we started with the Lorentz force and found the Lagrangian, but typically it is the Lagrangian that is usually given. And you will say that, oh, this gives me the Lorentz force. Okay, so that's, you will finish it as a small quiz, yes.
What?
Lagrangian is always off. It's not unique. If I get one Lagrangian, that's good enough. Okay, I choose this to be 0 if you. Okay, if that's what you're asking, this is a Lagrangian. How about that? A Lagrangian. And that leads to the question that, is it so, so what's the freedom you can have for the Lagrangian? So L, which is a function of x, v, and t, I can always add, this is a homework problem you will get. or you have in this homework. If I can add any function which has no velocity in it, but it is a total time derivative, it'll give me the same equation, same Euler-Lagrange equation. Okay, so I can add anything I want in here. As far as it is only position dependent, and it's a total time derivative, then my equations of motion does not change. And as far as my equations of motion does not change, I don't worry. That also again has this problem that can you hide some physics in there? Is there something missing? Sometimes often when you write a Lagrangian, you say, oh, this term is this term is that. Is there some issues with that? Like anytime there is not it's not unique, then the challenge comes on us that, okay, which one is this? What does this mean? So it becomes a little harder. That's the idea of algebra and geometry, if you want, that algebra is always gives you like a quadratic equation, gives you two solutions. Sometimes just visually it is hard to see that accuracy. So, okay. So that's Lagrangian. Let's now following. And let's go back to one dimension for a moment. Let's say L is having X as a function of time. It should not matter, right? So let me write X vector, velocity, and time. I define my Hamiltonian as X. Or let me, so let's say okay, the moment I have a Lagrangian, I have a canonical momentum, right? So that's Lagrangian. Then I have a canonical momentum. Always. Which we define here is given in terms of the Lagrangian. It's the gradient of the Lagrangian with respect to velocity. Not with respect to position, and with respect to velocity, and just now we did that. Now we define the Hamiltonian in the following way. H is equal to V dotted with P, or P dotted with V, either way, minus the Lagrangian. That's going to be our definition. This is also called a Lagrange transformation. In thermodynamics, you see this a lot, but for our purposes, this is just a definition. Hamiltonian is V times P and L. Remember, there is an action associated with this, and that depends only on X, correct? Not on velocity. For a Lagrangian, there is an action which depends only on X. Let's ask the question, what will this look like? Let's take it. So the way I have written, there is a V, now there is a new P. So it seems like H is equal. It can depend on X. It can depend on V. And now I have a new variable P, right? Right, that's what it is. Okay. But suppose I claim that it has no velocity in it. How will you check it? if I say a function does not have a variable in it, how will you check that? Derivative, right? If you take the derivative of that with that variable, it should come out 0. Okay. So the claim is that Hamiltonian in general, the way I have defined it, it seems like L has X and V in it. Then there is a P introduced in it. So there is a V, so there should be a V dependence in here. It's expected. But let's calculate this. So let's calculate the H by dV. So in here, it is just P. So I'm using this. So let me do that in 2 steps. I didn't need a second from that. Minus L. That's equal to almost immediately. This is P minus partial derivative of L with respect to V. What is that equal to? 0. And why is that? Because that's a definition of your canonical momentum, right? So that's 0 immediately, right? That's a simple statement here, but that means that this doesn't exist. You cannot have velocity dependence in Hamiltonian. You will often see that. So often you will see Hamiltonian written as P squared over 2m plus potential energy, right? It's convenient often to think of it as, oh, this is half mv squared plus u, right? Because kinetic energy is P. But Hamiltonian, in many ways, it's almost like a requirement that you write it in terms of P all the time. This is nothing wrong in it. Most of the time, P is mv. It is fine. It is safe. But this is velocity independent. You don't write it in terms of velocity the way Hamiltonian is defined. Especially if you're writing it as an equation. Okay. And the next question. So there is a
Wait, so the that's because momentum minus Lagrangian of velocity is also momentum.
so there will always be whatever velocity dependence is there in here, it will cancel this. So it seems like such a simple subtraction I'm making, but that will always kill it. Always kill the velocity dependence in there. This is called Legendre transformation. You use that left and right in thermodynamics. In thermodynamics, you construct a lot of energies. You have Gibbs energy, free energy, potential energy. All those transformations you always do in this manner. One is so this is called Legendre transformation. So at a time you're always having only one. So Hamiltonian then is what I can say is that it is R dependent or X, right? I'm writing X here, I think. X dependent and P dependent. No velocity dependence. It's also good to know. So Lagrangian has Euler-Lagrange equation as your equations of motion. What about Hamiltonian? Like, what are the Hamiltonian equations of motion? Here I will simply write it. We will see this somewhere else. So if I do, because in your homework you need this Hamilton equation of motion. And then maybe I'll do an example and then I'll stop. Is dx by dt is equal to partial derivative of the Hamiltonian with respect to momentum. And t by dt is equal to negative. Let's do an example. maybe 2 examples. And 5 minutes. Gravity is 1 example, so it's half mv square minus mgz, right? That's the gravitational potential energy. That's a kinetic energy. Everything is, let's say, happening along a straight line, vertically up and down. What is the canonical momentum? Immediately, you do dl by dv, that's mv. And then I can get Euler-Lagrange equations. So maybe d by dt of dl by dv is equal to dl by dz. This implies that d by dt of mv is equal to minus mg. That's Newton's law. But then you do Hamiltonian. Hamiltonian is equal to v dotted with p minus of the Lagrangian. That's equal to v times p minus the Lagrangian, which is half mv square minus mgz. As I said, Hamiltonian cannot have velocity. You have to replace velocity with p at this point. V is p, right? V is equal to p over m. So that's p square over m minus 1 by 2 m p over m square plus mgc, right? This is using the definition of p is equal to mv, right? Using the canonical momentum definition, and that's equal to, so Hamiltonian is equal to p squared over 2m plus mgz. The z by dt, Hamiltonian equations of motion, is dh by dp. That's equal to p over m. That's velocity. So this implies that velocity is equal to p over m, consistent with what we had earlier. Dp by dt is equal to negative derivative of the Hamiltonian with respect to z. That's minus mg. This is consistent with dp by dt is equal to minus mg, which is okay. That's an example which clarifies this whole construction. I have 2 minutes. I'll do one more example. Lagrangian, this is harmonic oscillator. Is there a class? Do you guys have a class? I'll not take too long. Plus minus, right? Of kx square. That's the spring p, canonical momentum, dl by dv. That's equal to mv. Again, Euler-Lagrange equation, d by dt of dl by dv, and there's also one more equation that dl by dx is equal to minus kx. That's equal to dl by dx. This implies that d by dt mv is equal to minus kx, right? That's Newton's laws. Hamiltonian is equal to v times v dotted with p times p minus of L, which is half mv square minus half kx square. Replace the v. V is p over m. Plus half kx square. Put this together, p square over m, so this is p square over 2m plus half kx square. And equations of motion, d x by dt is equal to partial derivative of h with respect to p. That's equal to p over m. Right, that's p times velocity is p over m, and the p by dt is equal to negative partial derivative of the Hamiltonian with respect to x, and that's equal to minus kx. Again, correct, right? So sorry for hurrying at the end, but I'm almost done. Thank you.